So now we have the finished prototype on a breadboard. All that's left to do to make this a complete product is to turn this into a schematic, which is the drawing of the diagram. So it's little block diagrams of, a block diagram for this chip, one for this chip, one for all these components, join them up with wires, and show them on effectively a piece of paper. That's what a schematic is. It's your visual representation of the hardware. After that, we just need to then do the PCB layout, so the actual circuit board layout, which is using that schematic file to then make the real-world connections to the physical chips that we use, which will be a lot smaller than these. These are big prototypey chips. When we come to do the board layout, they'll be the tiny chips. But there's basically schematic to do next, and then PCB layout, order, and we're good to go. The first round should be perfect first time. There's no real reason why not. It's a really simple design. So let's jump in and do the schematic, and then there's one video left, and this will go into market. So it's time to turn our prototype into a working circuit board and get these things ordered. So I'm going to recommend for everybody to use EasyEDA for the PCB layout. There's many options. The most common one is probably Eagle. Then you've got EasyEDA, you've got a bunch of other things. EasyEDA is free, it's useful and it's easy to use. And the main benefit as well is it can also open up Altium files. Now, because I pay thousands of pounds a year to use the top-end software, which is Altium, I'm going to design this in Altium, but you can design the exact same thing in EasyEDA. And once we're done, I'll also export it into EasyEDA, so you can use it yourselves as well. So even though I'm going to be designing in Altium, the process is almost identical in EasyEDA, and there's plenty of tutorials out there. So I'd recommend downloading this, opening it up, and you can kind of follow along as you go. If you really want tutorials on it, I can do tutorials on it in the future. So let's just jump over to Altium now. So the first thing I'm going to do is just make a new project. And we're going to call this one, if you've guessed from my product line, this one's going to be called Clean Light. So we'll make a new project. And then with this, I will now add a new schematic. So again, this is similar to EasyEDA. You will start with making a new schematic. I'll go through the whole process of this in depth in another video. This is just to get you into the whole process of how you make a product start to finish. So we'll go deeper dive in future, but we really want to see the process start to finish. So it might seem like I'm jumping over some topics, or how do you do this, how do you do that, but just focus on this one as starting to learn and understand how to make schematics and circuit boards. You don't need to know every single little detail, otherwise it'll take a lot longer to finish. As we start making more projects, we'll go more into depth of specific topics so you understand more about what we're doing. But for now, so long as you can follow along and understand the processes, you'll be good to go. So we have a new board here, and the first thing we need to do is chuck some connections in. So these will map to physical connections on the PCB, and that's what you'll see as we go. So I have some solder pads that I use to make connections. So we'll use this solder pad, and we need a few. So we've got one for ground, one for the 3-volt line, which is where the buttons are pulled high to, one for the 5-volt line, which will be connecting LEDs to, one for the start button, one for the select button. I think those are all the pads we'll need at the minute, so we can move this over. We can name this. What we'll do is say get a ground pad in. We'll just hide the word ground, and we'll connect this like this. So here's your ground connection. So this is indicating that whatever this is connected to is now going to be to ground in this schematic specifically. And we've gone to this test pad. So if I just quickly make a new PCB so you can see what is going to happen right at the start. So this would be a circuit board, and there's your big green circuit board with nothing on it, nothing defined and nothing on it at the minute. If I were to go over to the schematic and save this, also rename this to match. Everything's now saved. So now if I was to just import the changes, we need to name things first. Let me just delete this and show you what's going to happen. We just call this J1. Save this and import. You can see then what's happened is we just remove the room. We have this one pad now, which is a solder pad that I've made. And you can see on a PCB now it would act as a solder point, similar to what you've seen. So when we do things in schematics, these objects we're placing, say I just chuck on this random thing here, and we will name it U1, save and update the PCB. You can see now we have these components. If you go to a 3D view, you can see we have this little component here. So what we're doing when we make a schematic is every part that you make, and these are parts you have to make typically, will have a footprint. So you can see here it says footprint SOT353. So this physical flat layout maps to a real world physical part when we do the PCB layout. So when we're dropping all these things like this dot, it just looks like a circle. This is something I've made, and this is a component in Ultium. So when you see me dropping things on, that's what's going to happen when we map it to a PCB. Each physical thing we drop on turns into a real world object in here, and then we have to draw the lines. So let's just go back and put these connectors in. Let's wire this back up. So we have the ground connection. Let's move that out of the way. Next one is the voltage rail. So we're going to have two voltage rails. So we can do, say, this. We can just place a net, which looks like this in EasyEDA as well. We want two of them. Then we're going to name this one VCC_3V3 for the 3.3 volt input. And we're going to name this one _5VO, standing for where the V is, you replace it with a period for mean dot, so 5.0, 3.3. We wire these two up, and now we have two connections that we want to connect to the Game Boy's 3.3 volt and 5 volt lines, and the ground lines. So this will get us power, so if we make this match, this will get us power and ground into the system. So what I like to do, normally when schematics are bigger, but we might as well do it in this one and keep it clean, is I like to name and make things look nice. So we'll use some Arial font, Arial black, and we'll call this power input. We'll make the font a bit bigger, and we'll kind of section it off into here. You can then, once you've done your section, you can draw lines. You can see down here as well, you can do smart linking to get the title to update with properties, but for now, let's just put the title down here manually. And we'll do V1.0. So we have a title down here, make that a little bit smaller. And there's our little title. Got the power input up here, which we will section off like this, just keep things nice and clean. This then will be the start and select, so this could be button inputs. And similarly, how we did before, we have two connections, and we want to connect them to the start and select of the console. But because they're going to go basically directly from here into the NOR gate, we can name the nets, which again, we might as well start with all the good practices. So if I'm going to do this, let's actually use a wire. If I'm going to draw a wire like this and then place specifically net labels, and we chuck them on the lines. So these are wires, the blue ones, and we do that in Ultium with Control W. So this wire represents a physical connection between two parts, whereas this line is just drawn here with a line. So that's a line versus a wire, which is an actual connection. So this is just visual in the schematic for like literally drawing shapes, similar to text is. This isn't an actual component. Whereas these red things and the wires are all physical details that will end up on the PCB. So in this case, if I was to put in, let's just chuck in the NOR gate that we'll use first. and this is the one we're going to use. So I'll give you the data sheet to that in a moment, but here's the input and here's the NOR gate where you've got 2 inputs and 1 output. So if this is start and this is select, we could wire it up like this and directly wire, showing them going straight to the component. What you can also do that's exactly the same, and what helps to separate bigger designs, you can label the net like this and call this GBA start and GBA select, and then you can add a wire here and a wire here, and you can just copy and paste the net straight on like this. And now this is done the same thing as physically connecting them like this without the need to connect them. So these are net labels. We can then move this off out the way and design this kind of little chunk of the circuit separately to this chunk. So even though this is a small design, I'm going to purposely make it the way that you'd make bigger schematics, so you kind of get into the one, what you'll see in larger schematics and how to follow them and what they mean, and 2, just into some good practices. So we have the button inputs, and what did we do on the button inputs? If you remember, we added a resistor and a capacitor in order to slow down the input signals. So for that, we used, I think I used a 180k resistor. So I have one here. We can drop that in line with here, and what we'll actually do, because the signal coming in wants to be slowed, we'll actually do GBA start let's do this. I don't want the net name to be too long, you see. So see, that would be, yeah, we'll do that. We'll just call it GBA start slow. And then we'll just have to expand these wires and nets out a little bit. So we want the input into the NOR gate to be after the resistor divider. And then we'll do the same for the select. We'll place a resistor on the line. And then I think we did a 10 microfarad capacitor. So we'll use a 10 microfarad. That one is fine, standard. And we did this. We connected, if you remember, a capacitor through and to ground. And now because we want to make ground here, we can just copy this ground signal. And it means now we have, wherever this is connected, this is also connected. So when we solder this pad to the ground of the Game Boy, because this is connected to ground and we do the circuit board design, this point will also be grounded. So that's just how it's going to work. But you'll see this as we go. With this being your first design, just kind of follow along. So there's the input. And then we'll put another net label on here. And this one will be select slow. And I like to kind of get a bit of symmetry in the design so it looks neat. Move that out of the way. So now we have the button inputs. We can wire around it. And what we could do is simply drag this out and then add a line down. So it kind of blocks it off. Otherwise, the little area that we've got left is of no use anyway. And this can be moved over. And there's our 2 little areas. So far, you should understand that these are going to be the solder blobs on the circuit board that we wire to. So this is where we will connect. We'll probably do direct connections, but these will be good secondary points. So these will appear on the circuit board on the PCB as actual circles to solder to. And we'll join them to GBA start, select, 3 volt, 5 volt and ground. They're the inputs and the only inputs we need from the console. From that connection then of the start button, we pass it through a resistor capacitor circuit so that the capacitor charges up slowly and we get a slow change in signal here of roughly 1 to 2 seconds, which we can fine tune by changing either the resistor higher or the capacitor higher. And then we'll just about move on now to the first stage that we did, which was a NOR gate. So the one I'm using here is this QFN 16 package. So this is a much smaller package than what we saw on the breadboard. But if we jump to the data sheet for it, we have this one here. So you can see it's a tiny little chip. And if we open the data sheet, it's all the same spec. So we have pin 1 and 2 is A and B of the first input, and pin 3 is the output of 2, ground, and then 5 and 6 are the input of 2, 7 is the output of 1, and 8 is the VCC. All this is the same specs as the other chip we were using, so there's no real need to look too much further into that. And then if you see here, pin 1 and 2 goes to the input, 3 is the output of 2, 4 is ground, 5 and 6 are the input of 2, 7 is the output of 1, and 8 VCC. So obviously I've drawn this up, made sure it's all right, and I'll show you how to kind of create the components at a later date. In EasyEDA, you can actually search for components, and it does have quite a huge variety of already made components, so you might not have to make any, you could just possibly import this one. But we've got now the power input, the button input, and this is now going to be the signal to the flip-flop. So we could do this all on one circuit here, because really we're just inverting an input and output. We don't need to split this much further. What we want to do next is include a D flip-flop. So for that, I'm going to use this one. And again, if we just jump back to the data sheets, that one's done. This is the D flip-flop, and again, same specs. We're going to use a D flip-flop in this package, so it's a Exon 8 package, I believe. Yeah, actually, I think both are Exon 8s, not QFNs, but they're basically a small, tiny package, a few millimeters in size. We have the clock pulse, which stands for clock positive, the data, the not Q, the Q, the ground, the power, and then the two that we're going to ignore, which are the set and reset, or the not set and not reset pads. So we'll just double check as well on the NOR gate that we have the Schmidt triggers. And the way we do that, I'm sure we did, but let's just do a double check before we make any mistakes. Yep, you can see the Schmidt trigger action on all inputs makes it tolerant for slower rise times. And the hysteresis is typically 100 millivolts. You'll see further down normally when it's got Schmidt triggers that it will reference the high and low voltage as a percentage. So here, low level input voltage, it's a percentage of VCC. And it's also a percentage of VCC for the high signal, which is here. So basically, it's 0.3% of the voltage and 0.7% of the voltage. So we have Schmidt triggers in this chip as well. So we're good to go there. So that's the NOR gate and the D flip-flop. So let's wire these up like we did on the breadboard. So we've got the inputs coming in from the system already slowed down. We need to ground and power this chip. So it's always good to pay attention to voltage domains when you're working with board design. This chip is tolerant up to 5 or 6 volts, I believe it is. Same with this one. However, the signals are 3.3 volts coming in. So if we were to power this device from 5 volts, a 3.3 volt signal might not trigger 0.7% or effectively 70% of 5 volts. So we want to power this from the 3 volt rail. So to do that, we will take the VCC 3V3 and wire up the input. It's always good to tag designs as well. This is just, again, good practice, with a no connection flag. So if you are not intending to use this secondary NOR gate, instead of it, in case it was a mistake, you can set rules in some software like Altium. So say we were meant to connect to this pin 3 and we didn't, it could error out. If we explicitly tell it with these crosses that we don't want to use the inputs, then it won't error when we don't make a connection to them. Whereas 7 being an output and not having a red cross, it will error out when I try to compile the project due to the rules we've got set. So this red is simply telling the software that we're not going to use those pins. So we have the 2 inputs into the NOR gate, and now the output, if we remember, wants to go to the clock pin of the chip. So we could line this up neatly so that we can do the output straight into the data pin. Oh, no. The output straight into the clock pin, actually. And we could do that, so it looks a bit neater, maybe. Yep, let's do that. Ground again. Let's ground this chip. And power, we're going to do the same. Power it from the 3.3 volt rail. These are the not set and not reset pins, which we just tied high before. So let's just get a 47k resistor. And we will just tie these to high. So we'll tie them to the 3.3 volt rail. So they come out through the resistor, and we'll have them tied to the 3 volt rail like that. So there's two pull-up resistors to just disable them. If you remember, we're using the NOT queue into the data, which is conveniently right next to itself. So there's the loop around, which will turn it into a flip-flop. And now this leaves the Q output here. Now this will go out to a transistor to drive the LEDs. So at this point, because this section of the schematic has already got two components in, it's doing quite a bit, and we might want to annotate it and explain what's going on. I'm going to do a net label, bring out the output pin, which is what we want to use, and we're going to drop a net label on it. So let's just copy this, paste it here, and we're going to call this LED trigger or gate trigger, because it's going to go to a MOSFET. So this will now be the trigger that basically goes to 3.3 volts or 0 volts whenever we hold the two buttons down. So let's now move this into, say, this area here. We'll call this one button logic and trigger. You can call it whatever you like. That's just what I'm going to call it for now. Box this off. And if this got too big, you can also do multiple page schematics, but this is fine for now. So all that's left now is to, what we did in the breadboard was just chuck an LED straight on here, go into ground. But now we want to do it properly where we have a bunch of LEDs. So if we looked at the GBA, we want the A and B button, the start, the select, the 4 D-pad arrows, and the 2 triggers. So that's 10 LEDs we want on this design. So let's first get an LED. I'm just going to use a green LED for this, and I'll tell the factory what LEDs we want when we make them. It doesn't really matter any of these LEDs being specific, because we're going to place them on the circuit where we want. So we don't really have to worry about labeling all these LEDs a certain way. However, what we do want to do is make sure we do this the right way. So if we looked at the circuit by default, it would power up, and the default state of Q we'd expect to be 0. And we've observed it to be 0, so effectively ground. We could check the datasheet to see if it tells us a default state of the Q pin when it's not used. And there's nothing in the datasheet that tells us what it's going to be. But from observation on the breadboard, we saw that it was 0 volts. I'm going to presume this acts the same, and I can't see it triggering at a high voltage. It's going to trigger on the clock pulse, and there isn't going to be a pulse when we start up because nothing's pressed. And even if it was and we started up and these were low while the system started, it'd have to stay low for nearly 2 seconds to trigger a pulse. So this won't receive a pulse. So unless Q magically starts in a positive state, this would mean the trigger is going to be low. So we know the default state is going to be 0, and we want to make sure the LEDs stay off by default. So that means the LEDs want to be triggered high in order to turn on. So that will mean the gate of a MOSFET needs to be high to turn on. So all we need is an N-channel MOSFET. So let's just use one of these that I've used before. And this is the part number to the specific one. This will all be open source, so you can get all the details of all of these chips anyway. And the way a MOSFET works, you can think of it like a physical switch. There's a million and one different ways you can use transistors. There's multiple different types of transistors. MOSFET's one of them, BJT's another. There's lots of different types of transistors. The most common one, I'd say, and certainly what I use, is MOSFETs. And the way you can try and think of them is between drain and source, DNS, it's like a physical switch. And when gate triggers and says effectively turn on or off, drain and source connect. So it's a really oversimplified way of thinking about it. But that's all you need to know to start with. How do you know which side? Because MOSFETs can only conduct in one way. So you can only pass power through a certain direction. How do you remember that? Well, D stands for drain, so you can think of that as the thing that's going to drain the power. So these LEDs want to drain the power. And the source, naturally, you can think of it as the source of the power. So we know we need to source power, and something's going to drain the power. You've got N-channel MOSFETs, which is negative, and you've got P-channel MOSFETs, which are positive. So when it's an N-channel MOSFET, the power has to be negative compared to the drain. And remember, source has to be the supplier of power, so that has to be ground. So we have to ground the source. And the drain, the LEDs have to come in on. So we have to connect the LEDs to the drain. So the power is ultimately going to flow through, we're going to use the 5-volt rail. So the LEDs, because certain LEDs are going to be, say, blue, which are high voltage, you want to make sure you've got a high enough voltage level. So say you wanted to turn the LED on, you could do just this, connect it straight to ground. This would obviously blow the LED because there's no resistor. So there's just a LED. If we then got a resistor of, I don't know, you don't want it to be too bright, so let's say a 500 ohm resistor. Well, let's see what resistors I've got already made. Probably don't have too many that are low values. Let's use, say, a 680 for now. So the way you'd normally do it for an LED is you could just do this. And then what you have is the power, the LED with the flat line being ground, going towards ground here, and a resistor to limit the current. So this would be a basic circuit that turns a light on. So all we want to do is break this circuit here, which is exactly what we're going to do. So let's say do this. Break the circuit, and instead of going straight to ground, we put this switch in the way, like so. And now, when we trigger on gate, through this gate trigger, we join this connection here. And then the power flows through the MOSFET to ground. And remember, because this is an N-channel MOSFET, the source has to be lower than the drain. That's the basic rule of thumb. So 5 volts is higher than ground. On a P-channel MOSFET, the source still has to be the side that doesn't have any load on. That's where the power is going to come from. And the drain has to have the things that want to be powered. So a P-channel MOSFET will be flipped around. The source would be at the high voltage, and the LEDs would be below ground. So again, we're going far too deep into transistors for what we need for now, but this is the basic explanation as what's going to happen. So this is wired up now as a single LED, and then it leaves the question now, what do we do with gate to tell the MOSFET to turn on? Well, every MOSFET has the same rule. When the gate is closer to drain, so it goes towards the drain, it turns on. So while gate and source are the same, so if we were to say just ground the gate like this, the MOSFET's off because gate and source are effectively the same. As gate pulls away from source in the direction of drain, which means in this case, as gate gets closer to 5 volts and further away than source, so greater than source, the MOSFET turns on. The point at which it turns on is different on every MOSFET, and again, we won't go into too much detail, but on average, they turn on usually about 0.7 volts away from source. You can be found in the datasheet, but we won't dig into that. We know that 3.3 volts is well above the voltage of a MOSFET to turn on. So all we need to turn this on is to pull gate higher than source by at least about 0.7 volts. Well, this gate trigger is going to go to 3.3 volts because it's powered by this rail here. So if we simply just copy the gate trigger and connect it to the gate of the MOSFET. This means now when we hold the buttons down for 2 seconds, it triggers a pulse on the clock pulse, which toggles Q from low to high, which effectively toggles the gate here to high, to 3.3 volts, and turns on this MOSFET, which allows the LEDs to pass through and connect to ground and turn on. When we hold the buttons again, it goes through the same process, comes out, the gate trigger changes to ground, so gate and source become equal, and the MOSFET turns off, turning off the LEDs. So that's how it's going to work, and this is the little circuit to turn the LEDs on and off. So all we need to do now is make 10 LEDs. And the resistors and the brightness we can play with, but I do know if we have 220 ohm, the lights are going to be really bright. And I'm not sure how much we want super bright LEDs, they might be too much in your face. So I'm just going to leave 680 ohm on here as an average figure. They won't be too bright, and I don't think they'll be too dark. And if they are, the schematic won't change anyway. We could technically update the schematic, but all we'd have to do is just tell the factory to place the resistors in. And the resistors are also likely going to change value with the LEDs that we use. Red LEDs, for example, break down at a lower voltage, so we'll need a higher resistor to be the same brightness. So I'm not going to worry too much about this value. We're just going to get the boards ordered and then play with the resistors and decide how bright we want the LEDs to be. So all we need to do is make 10 copies of this, and all of them need to connect to this point here on the transistor. So if we just copy, what we can do is if we just disconnect the connections there, and we don't really want to see the color either, so it's nice and compact. If we do this, 1, 2, so if we just wire up and over, down to there, and then connect every LED and every LED to the drain of the MOSFET, you can see there we have now a big string of LEDs, and that's what will light up. Let's then just draw a box around this, and we basically have our circuit there. So we might have made mistakes here, we might have connected things wrong or overlooked something. So it's always a good idea to review your schematic again, thinking about the start point, where things are coming in, make sure you've got grounds, make sure you've got all your connections right. So you finish your design and we start here. So start with the power input. We're defining 2 arbitrary rails here, which just allows us to make connections later in the schematic like this, and it just means they're going to be, wherever you see the same value, they're going to be connected together. So we've defined that we've got a 3 volt and a 5 volt rail, and we've made connections here which turn into dots in the PCB. So we can connect to 3 volts of the GBA, 5 volts of the GBA, and ground. We can also connect to the inputs of 2 buttons, and that's all the inputs from the console that we have, which I think is right. We just need to get the power and know when 2 buttons are pressed. We slow down both buttons through a resistor capacitor network. This is called GBA start and start slow, GBA select, select slow, GBA start slow, and there's a mistake straight away. GBA select, we didn't update this to GBA select slow. So that would have been connected to this side, and then it would have been wrong. So hence the reason to overview schematic. So the 2 slow connections come in to the NOR gate, which we can click and check it is a NOR gate, it's a logic level gate. We scroll down, we can check the part number. We can check it is a NOR gate, so we've got the right part. It's powered from the right rail. The output goes to this chip, which again, we can check the properties of. And it is a latch and flip-flop. And it says right there, single D flip-flop with set and reset positive edge trigger. So that's the right part. We tie data to not Q, which is what we did on the breadboard. It's connected to the right power rail. Not set and not reset are pulled high, which is correct. And the output is called gate trigger. We then go to LEDs. We have what should be an N-channel MOSFET, which we do. And it can sync half an amp, 500 milliamps, which is within our limits because we have 10 LEDs, the maximum brightness of the LED will be 20 to 30 milliamps. That'd be 300 milliamps. And we don't intend to, I don't think, run the LEDs at maximum brightness. They'd be quite intense. So this should be well within spec. We could go to a higher one, but I honestly think this is well within spec. Gate trigger goes to gate. Source, which you remember is the thing sourcing the power. And in an N channel, source is always more negative than drain. We've got connected to ground. The LEDs are on the 5-volt rail, not the 3-volt, because certain LEDs like blue need almost 3.3 volts to break down. So if we powered it from the 3.3 volt rail, it might not light up fully. And then we've got resistors on every LED, which we can tweak to our liking. And I think that is it. You'll notice none of these ports are numbered at the minute. So we have J question mark, R question mark, C question mark. They all need individual identifiers like R6, R14, C12, U1, and that's what you see on circuit boards. In Altium, I can label these automatically when I'm finished. So I just need to go to Tools, Annotation, Annotate Schematic, and then Update List, Accept Changes, and bring them in. And it will automatically label them all for me. So now it's labeled them J1, 2, 3, U1, U2. You can see everything's got a little name now, D1 to D10. It's all been labelled. So that's the schematic all done. Hopefully you can understand what this schematic is compared to the breadboard. You might not fully understand how to make the internal components yet, or fully understand a transistor, but you understand the whole concept, and you've seen it on the breadboard before doing this. So this is the schematic all done and ready to go. And let's now just jump straight in and let's get the PCB designed.